Okay, hopefully this is going live. It hasn't told me that it has yet though, but hopefully, oh, there we go. I think we're on. Lovely. Hello, welcome everybody. Sorry, my laptop is sometimes a little bit slow, so I'm sometimes not sure if it's actually streaming yet, but hi, how is everybody doing? Please feel free to say hi in the chat. It's nice to see lots of people already here and already chatting about school and stuff, so that's really nice. But welcome to Sunday sessions, A-level chemistry Sunday sessions. We're looking today at alkanes is going to be our lesson today, so hopefully you guys are all ready to answer some questions about alkanes. I'll just get my PowerPoint shared now. I know it's working or it's up, but hello. Those of you who haven't met me yet, because I've not done an A-level Sunday session yet, I'm Alyssa. I'm one of the chemistry tutors. My kind of current main time is spent, actually it's split half and half between GCSE and A-level, but I haven't done an A-level Sunday session yet, so this is exciting for me. But nice to meet lots of you. It looks like there's loads of people here already, which is really nice. And hopefully my PowerPoint has just shared itself with you. I think it should have worked. There we go. Hopefully everyone can see that then. Please let me know if you can't see my PowerPoint being shared. I'll just sort that out now that that's ready. How is everybody doing? Is everyone all right? We'll just give it another kind of 30 seconds just to see if anybody else wants to join us for the beginning of the lesson. But it's nice to see everybody. Like I say, welcome to our A-level Sunday sessions. This is a lesson on alkanes. If you haven't already, please feel free to download the slides, which are in the description. Thank you very much, Sadaf, for saying now you can print them off, all these kind of things. It means that they're very useful, or hopefully are going to be very useful to you now and in the future. So please feel free to download those. But yeah, I think we're probably ready to get started. So some of you, it seems as though some of you already know each other. So I'm guessing you've been to a few of these sessions before. But a little bit about me before I talk about these sessions. I am Alyssa. Like I said, I'm one of the tutors at SnapRevise. I'm the lead GCSE chemistry teacher, but Oxford, and I've been teaching and tutoring A-level chemistry for the last 6 years. So really enjoying chemistry. Chemistry is my favourite, but I do like all the other sciences as well. And yeah, that's a bit about me. The 1 week free trial we have is, oh, my screen's got a bit, it's frozen itself, I think. We've got, oh, it seems I'm breaking up a bit. Oh, I don't know if you guys can still hear me yet, but it would appear that my Zoom has frozen. Oh, you can still hear me. Okay, it was just the video then. So it might have come back. I don't know if you can still hear me. Okay, you can hear, oh great. You can hear me, but you can't see me. Okay, lovely. It's okay. So it just had a moment. It had a funny, couldn't cope with me starting the slides apparently. We'll try again. How's that? Everyone happy? Okay. You can see the slides, but face is frozen. That's a little bit better. Okay, the camera's frozen. Should we turn, the slides are good. Well, Okay, I might turn the camera off then, just whilst we do this. Oh yeah, it has definitely frozen, hasn't it? Okay, slides are good, camera's frozen. So I will turn the camera off when my Zoom wakes up. Oops, or I won't. Oh, dearie me. Yes, well, I'll just turn the camera off so that my laptop stops freezing, and then I will let you go, then we'll get started. But it hasn't, silly thing. It can't cope. Oh, dearie me. Come on then. I'm just trying to turn the camera off, but my Zoom has frozen, so you guys can probably still hear me, but I can't do anything. So, oh, right, let's try this now. It looks like it's just returned for me, so hopefully this means, no, I can't do anything, I'm afraid, guys. Sorry, my laptop is completely frozen, so we will get there. We will get there. It's just taking a couple of minutes. It's just having a funny. Decided it doesn't want to play ball today. You can still, yeah, so as soon as my laptop starts responding, then we can get on with the lesson. And I'll turn my camera off and we can keep going. But at the moment, I have no control over my screen. Oh, this is good fun, isn't it? Technology is absolutely incredible until it goes wrong. I mean, if you think about where we've come, and I'm just rambling now, but if you think about where we've come in terms of this being able to teach over the internet in such an interactive way, I mean, I think it's awesome, but it does mean that as soon as technology stops working, that's it. Are we back? I can't tell if we're back. Oh, yes. Yay. Yay. Fantastic. Right, I'm going to leave just to make sure that it doesn't try and crash on me again. I'm going to leave my camera off for now. So you'll just have to cope with my voice and I'll do all my gesturing to nobody. Cool. Lovely. Right, let's try that again then, shall we? Just means I'm going to have to speed talk a bit or speed push through. Thank you everyone for being so brilliantly patient in the chat. That's you are brilliant. So thank you so much. Looks like we'll just be stuck with just a PowerPoint. So that's fine. Fabulous. Okay, so I was talking, welcome back, thank you very much. I was talking about our 1 week free trial. So if you are interested in trying out the tutoring program on SnapRevise, then we're offering a 1 week free trial. So you can go on to snaprevise.co.uk and I'll show you at the end. If you go on snaprevise.co.uk and use tutor7 there, which is a code which expires in 24 hours, then you can get 1 week free trial for the tutoring. So we'll go through it I'll go through that a little bit more at the end, but hopefully some of you might want to take advantage of this 1 week free trial. So yeah, the discount code tutor7 gives you a 1 week free trial. Okay, so this lesson, obviously it's going to be slightly lesser now, and now we've had all that faffing, but never mind. We are going to look at understanding trends in boiling points of alkanes, of the alkane homologous series. We're going to recall the processes of fractional distillation and cracking, but we're not going to spend too long thinking about it unless there are some major questions. And then we're going to recall the equations for combustion of hydrocarbons and other pollutants. We're not, however, going to look at branched alkanes, which is specifically OCR, thermal cracking, which is specifically AQA, or reforming, which is specifically Edexcel. So good question. Is it private tutor lessons? It's not private. It's 1 to between, we normally have on average, well, it varies hugely, but between 4 and 16 tutees or students in the room. It does completely depend though on the day, the time, the lesson, etc. So sometimes there are much smaller groups, sometimes there are a little bit bigger groups, but it's still very interactive and very useful, I think, for getting questions answered. Can tutors give predicted grades? Not likely. We can kind of gauge how quick you are at giving answers and the kind of use of words that, or use of keywords, your use of keywords, but because you could very easily be Googling things or you could have your textbook open, etc., it's not very easy for us to give predicted grades. And we cover all topics. We cover the whole specification for AQA, Edexcel and OCR across all of the A-level sciences and maths. That's just to answer Flo's question. Okay, so if you haven't joined us on these before, we provide at the beginning of our lessons, especially our web classes, the specification points that we're going to be covering. So for AQA, these are the specification points that I am going to be covering today. These are the OCR specification points I'm going to be covering today. And then these are Edexcel specification points I'm going to be covering. So if you have downloaded the slides, then you can keep flicking back to your exam board and double check that you're happy what you need to know. If they've got any questions or anything you don't understand, then you can ask and we can try and go through it together. So let's have a look then. What do we already know then, guys? What is the definition of a hydrocarbon? What's the definition of a hydrocarbon? And if you can remember, what's that key word that you have to put in to get the mark? What is the definition of a hydrocarbon? And can you highlight to me what the key word is you need to say? You can download the slides from the description in my in the YouTube description. Fantastic, good, lovely. And I think everybody has used the word only, and that's brilliant. We have to use that word only. So a hydrocarbon is a compound that contains, I'll try and write properly, only hydrogen and carbon atoms. So really well done, those of you who put that. If at any point you can't read my writing, by the way, please let me know, because I will write out again or I'll explain what I've put. There you go, the link for the slides is in the description, is in the chat for you, so you can download it, but really well done. And I think, like I say, everybody has highlighted this word only. You have to say only to get a mark, or you need to at least imply it in your wording that it's only hydrogen and carbon atoms. Okay, general formula for an alkane then. What is the general formula for an alkane? This is the one which has got N in it instead of numbers. Nice one, guys. That's looking great. Fantastic. CnH2n plus 2. So you always have twice as many hydrogens plus 2. So, for example, we would look at C3H8. 2 lots of 3 is 6, plus 2 is 8. So we've got 8 hydrogens for every 3 carbons. Fantastic. Well done, guys. That's looking good. Okay, and now our alkane nomenclature. How many of these can you name? And feel free to give me as many as you want. So we've got 1 carbon, 2 carbon, 3 carbons, 4 carbons, 5 carbons, and 6 carbons. What are the prefixes that we need to know, or should, or hopefully already know? Fabulous. That's looking great, guys. Lovely. So meth, eth, prop, bute, and then we get into the slightly bigger ones, pent. So methane I should put, shouldn't I? Ethane, propane, butane, pentane, and the final one is hexane. Well done. Lovely. And just a way of remembering the first three, I've always used mice eat peanut butter. Meth, eth, prop, bute, MEPB. Mice eat peanut butter. But hopefully you can remember them already anyway. Lovely. Well done, guys. Okay. So first bit of content then, our part one is looking at the properties of alkanes. So what properties are important? So to begin with, like I said, we're not going to look at branched alkanes. We're just going to, at the moment, look at unbranched alkanes. So what intermolecular forces are present between unbranched alkane molecules? What are the intermolecular forces that are present? Nice. Yes, you're right. In year 11, this was very complicated, but actually when you are at A level, it's not that bad. Good, fantastic. I think actually we've got all the different examples of it, so good. So we're talking about London forces, but you may also know them as van der Waals. Van der Waals, and we can describe them as, I think somebody has in the chat, as dipole-dipole or instantaneous induced dipoles forces. So very good. Yeah, van der Waals, lovely. So these are London forces only. We don't have any other type of intermolecular force present in an unbranched alkane or in a straight chain alkane. It's only London forces. That's the strongest intermolecular force. Are London forces weak or are they strong? And therefore, how much energy is needed to overcome London forces or van der Waals forces? Good question. Why is it London forces? Not sure. Yeah, we should be trying to use the word London forces. You're right. I can't remember who it was that said that, but you're right. We should be trying to use the word London forces. Fantastic. So they are not very strong. So we only need a small, only a small amount of energy. Amount of energy is needed to overcome them. Fabulous. What about then, what can we see? Fabulous. I think some of you have already said it already because you know where I'm going with this. What happens then as our number of carbon atoms increases? What happens to the intermolecular forces as our number of carbon atoms increases? Lovely. Yeah, good. Fantastic. So the longer the chain, i.e. the more carbon atoms there are, so the longer the chain, longer the carbon chain, I should say, the carbon chain, the more interactions or forces there are. And actually, the greater those forces are as well, and therefore more energy is needed to overcome them. Fabulous. Please feel free to ask questions in the chat. I know some of you have been already, which is awesome. If I miss it, because obviously the chat does go quite quickly, so apologies if I miss your question, just feel free to ask it again as many times as you need until I manage to see it. I do try and check the chat quite often, so please feel free to ask questions, and also please feel free to answer other people's questions as well, because that is very useful, very useful. It says it needs only a small amount of energy is needed to overcome them. So the longer the carbon chain, the more interactions or forces there are, and therefore more energy is needed to overcome them. Not to break and make new bonds. No, we're not talking about breaking bonds or making bonds here. AQA, I think you should be probably saying London forces. They sometimes are a bit nice to you and allow you to say Van der Waals, but I would try and stick to London forces if it were me. We're kind of trying to move towards calling them London forces rather than Van der Waals. So just to try and be clear. Okay, what about then? No, so your teacher might have introduced them as Van der Waals, which is fine because they are what we use to describe the same interaction. Lovely. Yeah, fantastic, guys. Okay, so next slide then, fractional distillation. The differences in boiling points of alkanes can be used to separate them by mass from crude oil. Hopefully you guys have seen this at GCSE. So we're going to have crude oil going in at a really, really hot temperature. And I'm just going to change my colors. So the one thing I always remember about fractional distillation columns is they're backwards to what we would normally think about. A hot is at the bottom. Oops, didn't mean to go backwards. And then our cool or colder is at the top, which is backwards compared to what we would normally consider for something, because we normally think about hot things as being less dense, so rising. But in this case, it's the other way around. Hot is at the bottom, cool is at the top. Yes, London forces are induced dipole interactions, Brandon. Yeah, good question. There we go. Okay, so what do you know then about the size of the molecules in a fractional distillation column? What do you know about the size of the molecules in coming out of a fractional distillation column? Where are the smallest molecules going to come out? Are they going to come out at the top or the bottom? Where are the largest molecules going to come out, top or bottom? Good, well done, absolutely. So it's our smallest at the top, usually our gases. Molecules sometimes come off, sometimes some still come off, or we could say shortest chains are at the top. So for example, our gases, methane, for example, and then our largest molecules or longest chains at the bottom. For example, things like tar, bitumen, etc. Yeah, brilliant, exactly right. So our long molecules at the bottom have a much higher boiling point. Our small molecules at the top have a much lower boiling point. Fabulous, good. Do we need to know the uses of each fraction? I would say it's unlikely that they will offer you marks, but it's not impossible. You are supposed to know what the fractions are and what their uses are. As somebody who struggles to memorize things anyway, I don't like the idea that we have to commit these things to memory. However, I think they could ask you questions on it. So let's say yes for now. Cool, lovely. So we're thinking then hydrocarbons are going to be separated by condensation or by condensation at each of their different boiling points. Do you do this in OCR? I would need to double check. Have a look at the front slides. I don't think you would do fractional distillation, but I think you would need to talk about, in the same way that we were looking at chain lengths affecting the boiling point. So this is an application of what you need to do, if that makes sense, for OCR. I'm not sure that fractional distillation is fractionating crude oil is specifically mentioned though. But in this case, hydrocarbons are separated by condensation in the distillation column. So you would do distillation, fractional distillation, just maybe not specifically with crude oil. Oh, can't spell column in the destination column at a temperature below their boiling point. Oh, can't spell below either. Below their boiling point. So that is the idea of a fractionating column, that it gets cooler as you go up, and as you go up, as the gases that have been inputted in from the hot crude oil cool, then at some point they will reach their condensation, their boiling point. They will condense because they would have gone below their boiling point, so they will condense into a liquid, and then we will collect them out as a fraction. Lovely. Yeah, exactly. Yeah. Good. Well done, guys. Fabulous. Okay, so catalytic cracking. This is, again, something which varies a little bit between exam boards, but we all need to know the basic concept of it. So longer chain hydrocarbons can be broken down into more useful compounds using cracking. So we use this term useful because often the examiners are looking for the term more in demand. If they ask you a question about what's the point of cracking, it's because you want to create some compounds that are more in demand, ones that we want to use more often, so more useful. Okie dokie. Yeah, exactly, Flo. I totally agree. It does seem so. When you did this did fractional distillation at GCSE, you think it's absolutely mental, but it's because you've taken your knowledge up a level, hasn't it? So the two compounds, or it's likely that we're going to produce ethene. Can you tell me then, I'll just do an impromptu exam question, what is the name of the molecule? If I produce ethene, what's the name of the molecule, the other molecule that I'm going to produce when I've cracked? So we often, not always, but often form ethene when something cracks, when we crack a long chain molecule. In this case, what's the other molecule going to be called? No worries. No, welcome. We have started, but please feel free to download the slides and join in. Oh, we've got some differing answers, but it looks like most people are absolutely correct. It would be pentane. So we would kind of break that bond there. That means we're 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 with all of the hydrogens, which is a fun exercise when it takes the pen a while to show up on my screen. I can't see where I've written, but there we go. That wasn't awful. That's not too, oh dear, that's a little bit awful. Lovely, fantastic. So that would, in this case, produce pentane. So we produce two different molecules. Why do we use a catalyst for cracking? Why do we use a catalyst for cracking? Yeah, good. Well, yeah, well done, guys. Hannah's asked, how do we know that there's 5? Because there's 7 carbons overall. So if we've used 2 of them for ethene, then the other one must be pentane, must be the other 5. Good question, Dominic. Why is it not an alkene? Well, if you count the hydrogens, we don't get rid of any hydrogen. So we only actually need to lose one we only ever need to create one alkene. You could kind of think about it as kind of cutting there. So a hydrogen joins the pentane to form an alkane, and then our alkene is formed by just using 4 hydrogens in the 2 carbons. Good, fantastic. Well done, guys. So those of you that are answering questions about a catalyst, we're using a catalyst because it's going to, so it speeds up the chemical reaction, speeds up rate of reaction by providing alternative pathway. With a lower activation energy. And so in this case, it can reduce the need for high pressure and high temperature. High pressure and high temperature. And anyone know what the catalyst is that we use for cracking? What is the name of the catalyst, or what metals are used for cracking? So Vasu, the hydrogen that was left out is included in the pentane. It's the end of the chain carbon on the pentane, end of the chain hydrogen, sorry, on the pentane. Fantastic, well done, guys. It is a zeolite catalyst that is used. Catalyst, which is aluminium and silicon oxide. So silicon, oh, I'm having to write really small, apologies. And aluminium oxide. Ugh, I did not leave myself enough space there. Nice one. I'm not sure. I have only heard specifically of aluminium silicate being used, so aluminium and silicon oxides. Whether or not you could use iron, I'm not sure. I think you'd have to do a bit of investigating that yourself, but I don't recognise that as being used. Okay, so how is everybody feeling? How is everyone doing? We are a couple of minutes behind schedule, but that's fine. We can cope with that. How's everybody doing? Activation energy. Activation energy is the energy required for a successful reaction when two particles collide. So it's the energy needed to start a reaction. That's what activation energy means. So if a catalyst provides an alternative pathway with a lower activation energy, it means the reaction can happen in a different way that doesn't need as much energy. And if it doesn't need as much energy, that usually means more particles can react, and hence we get a faster rate of reaction. Lovely, thank you guys. So this is just, and as lots of you have seen, this is just so that I can see how we're doing and I can gauge how everyone's feeling. So if everyone's feeling good, then that is awesome. Lovely. And if you're not, then that's absolutely fine as well, of course, but it's just so we've got an idea. Lovely, my pleasure, absolutely. Brilliant, fantastic, guys. Okay, so let's have a go then at an exam question. Feel free to stick some sentences in the chat. It says, outline the essential features of the fractional distillation of crude oil that enable the crude oil to be separated into fractions. So for those of you that feel able to, do you want to pop some sentences in the chat? What are the key features, or the essential features, sorry, of fractional distillation that mean we can separate it into fractions? Lovely, good. They need to have different boiling points of varying, good. Our varying chain lengths have different boiling points. Our fractionating column has a temperature gradient, fantastic. And therefore we have different boiling points. Lovely, this is all great, guys. And the final thing is we just need to say which one it goes where. So does fantastic. And I think Romy's just said that as well. Brilliant, so let's write that down. So our separation depends on different boiling points of hydrocarbons. Whoops, let's spell that properly. Carbons, which is dependent on the MR, or chain length, of the hydrocarbon. Then we've talked about temperature gradient. So there is a temperature gradient through the column, and I think you guys said that it is hot at the bottom, cool at the top. Or you could say it gets cold, you can say it gets cooler as you go up the column. Something like that would be absolutely fine. And then we've said higher boiling points condense at the hotter bottom. That's a great phrase. And lower, to bottom, and lower boiling points condense at the cooler top. And then we can also say gases leave, or actually no, I'll change that, I'll say lowest boiling points. Lowest boiling points leave the column as gases at the top. So that's probably more than I needed to say, or in more detail than I needed to say, but I want to make sure I get my 4 marks. So we talk about separation depending on the different boiling points, which is dependent on the chain length. The temperature gradient gets us a mark, and then higher boiling points at the top and lower boiling points at the bottom gets us our final mark. Lovely. So that looks fantastic. Yeah, so Romy, I've just said I think you would get 1 for talking about the different boiling points, 1 for talking about what the boiling points are based on, 1 for talking about the fractional distillation column, and so it's set up being hot at the bottom, cool at the top, and then 1 for saying why that then means our substances condense. Yeah, we could talk about chain lengths as well, so you could add that in to higher boiling points / longer chains. Actually, that's a nice idea. Lower boiling points, shorter chains. Yeah, I think that's a nice idea. Yeah, good. Brilliant. Okay, next question. Oh, my thing. There we go. Next question then. So this is what I was talking about earlier, about what you would want to say if you were asked a question about cracking. So C8H18 is obtained by the catalytic cracking of suitable heavy fractions. State what is meant by the term cracking and name the catalyst used in catalytic cracking. Then write an equation to show how 1 molecule of C14H30 is cracked to form 1 molecule of CH18 and 1 molecule of another hydrocarbon. Explain why oil companies need to crack suitable heavy fractions. So there's kind of 4 things here. 1, 2, 3, 4. And that's where we're going to get our marks. So we're looking, the key thing, so what is meant by the term cracking? It is larger molecules are broken into smaller molecules. And that's basically our definition of cracking. Definition. So that's our first mark. Then it says name the catalyst used in catalytic cracking. So that would be our zeolite catalyst. Then it says write an equation to show how 1 molecule of C14H30 is cracked to form 1 molecule of C8H18. So what else is going to be produced then, guys? If we produce C8H18, what else is going to be produced? Well, brilliant, well done. Zeolite catalyst. I think you probably should know zeolite in AQA, from what I remember. Oh, we've got some differing numbers going on. Just double check your maths. It should be C6H12 because we're literally just doing the maths. 14 minus 8 gives us 6 and 30 minus 18 gives us 12. So we should have 6 carbons, and 12 hydrogens left over. So that's another mark. And then finally, our final thing says, explain why oil companies need to crack suitable heavy fractions. So our heavy fractions are cracked. Why then? Why are they cracked? What's this key phrase? So you're right, Zara, the smaller molecules do tend to be more volatile and burn more efficiently, but that's not why we crack it. I think in the end it is, but the reason is, yeah, because they're more useful or more in demand, and that's what they tend to be looking for in an exam, which is a bit annoying, because I think you're not wrong, but we have to say that it's because smaller molecules are more in demand or are more useful, you could say, but I think more in demand is a good phrase to remember. So then we've got 1, 2, 3, 4 marks for the 4 different points in the question. Fantastic. Yeah, well done. Good, good, guys. How are we doing for time? Oh, not talking fast enough. Okay, let's move on then to combustion of alkanes. So complete combustion. Can you have a go at writing either the methane or the propane combustion? Pick one and have a go. Good, I'm glad it's useful. So can you have a go at writing a balanced equation for either methane combustion or propane combustion? So just double check that we're sure. Methane is CH4 and propane is C3H8. Then combustion. Combustion is always the combination of our substance with oxygen. So we have to add oxygen in to both of them. And our products of combustion, and we're assuming complete combustion here, as is written at the top. So we're assuming complete combustion. So our complete combustion must produce, that's it, carbon dioxide and water, as you guys have put. And then it's just a case of balancing them. Now, I haven't balanced those top ones yet because I was just going to do a general combustion equation, which you are welcome to remember, but you don't have to. You can just work it out on the day. That is obviously absolutely fine. But if we have a general combustion equation, why have I done that the other way around? No idea. Let's make it easier and do it that way around. If we look at doing a general combustion equation, it can make it slightly easier. If we've got X numbers of carbons and Y numbers of hydrogens, then we can do X plus Y over 4 oxygens, and it makes X numbers of carbon dioxides and Y over 2 numbers of waters. And that's quite a nice general way or general formula for working them out. So let's just double check that that works. So X plus Y over 4 oxygens gives us 2 oxygens, and X carbon dioxide is just the 1, and Y over 2 is 2 waters. So that should be our balanced equation. And it seems to agree with what lots of you have put. And then similarly, X plus Y over 4 oxygens for propane would be 5. We've got X numbers of carbon dioxide and then Y over 2, which makes 4 lots of waters. Lovely. Well done, guys. Okay, so that's complete combustion. What about incomplete combustion then? What's the difference? What's produced in incomplete combustion? So this is incomplete combustion. There are 2 different things we could make. This is not AQA, by the way. We can make carbon monoxide, which is a poisonous, or we could probably say toxic gas. That's CO. And soot, which is just C. Now, if you get asked this in a question, they should tell you what else they want you to add into the reaction. They shouldn't just leave you hanging, because you can obviously have differing amounts of carbon monoxide, carbon dioxide, or some or none produced. So just bear in mind that they should tell you in the exam, they should be giving you hints as to what is produced. So we've got carbon, which is just solid, soot, which is solid carbon. And then we can just balance it again. So that should be 2 of those and 4 of those. So this is our soot and this is our carbon monoxide. Yes, you can have unburnt hydrocarbons as well, but we're not going to go through that today. So this is incomplete combustion. Lovely. Okay, and then our final thing that we need to look at, which is not OCR, so you can have a 5-minute break if you are OCR, is pollution. We need to be aware that nitrogen oxides and sulfur oxides can be produced. So nitrogen oxides we would sometimes call NOx. It doesn't matter, it means that it's either nitrogen monoxide or nitrogen dioxide, etc. And these are found or come from the air. And our sulfur oxides, again, SOx, come from impurities. So we need to be aware of this. Good. Yeah, well done. So there are different, you have to know a couple of different reactions. So if our nitrogen oxide, if our nitrogen comes from the air, then it's just the combination of nitrogen and oxygen. But that usually, to begin with, just forms NO. But it has to be at a high temperature. This is why this doesn't happen in the air, just normally in the air, because in a car engine you have super, super high temperatures. So when you've got super, super high temperatures, the nitrogen from the air and oxygen from the air can combine to make nitrogen monoxide. And then these nitrogen monoxide molecules can combine with oxygen again to make NO2. And what's the issue with NO2 then, guys? Why is this a challenge? Is this in Edexcel? I'm not 100%, Maya. So if you're talking about the international A level, I think it probably is, but the I, yeah, I think it is. The I, oh no, that's Cambridge International, never mind. I would assume so. Yeah, good. Acid rain, so it's acidic when in solution. So it can produce acid rain, or contribute towards acid rain, I should say. Lovely. And then with our sulfur, which is a solid, it can combine with oxygen to make sulfur dioxide. And then what happens, guys? What's the issue with this one? What's the issue with sulfur dioxide? Because it can then go on to do what? Yeah, nice. It then combines with water and oxygen. And again, acid rain too. Yeah, exactly right. Then produces H2SO4, which obviously contributes towards acid rain as well. So doubly bad, both of these, or not very nice anyway. Oh, I haven't balanced my equation, have I? That's half there. Fabulous. Okay. How are we doing for time? 5 minutes. Cool. 5 minutes for questions. That's not too bad. So that's just content. I think you just have to learn it. There's not a huge amount to kind of understand there if you're okay with normal reactions and reaction mechanisms and balancing equations and stuff. So unfortunately, you just have to try and memorize that. But let's have a see how everyone is feeling about it anyway. Yeah, exactly, Rosie. I like that as well. It can damage aquatic environments. We don't want acid rain because it damages aquatic environments. It can disrupt soil pHs. It can cause erosion, chemical erosion, all this sort of thing. Or chemical weathering, actually, I should say, not erosion. Chemical weathering. Yeah, exactly. So let me know how you're feeling at the moment. Are we feeling good? Are we feeling all right? Or are we feeling super confused? Or somewhere in the middle? That is obviously absolutely fine. Good. Lovely. Okay, let's see if we can do at least maybe one page of questions on this then. So, exam questions. Write an equation for the complete combustion of pentane. State symbols are not required, so that's good. So write an equation for the complete combustion of pentane. Can you show me an equation for the complete combustion of pentane? No need for state symbols. What do you think? What is an equation for the complete combustion of pentane? So pent being 5 carbons, so hopefully we are happy that it's C5, and then it's got to be H2N plus 2, so that makes H12. And it's complete combustion, so we're combining with oxygen. And again, it's complete combustion, so it's, yes, Candy, I mean, it does specifically say right. They are sometimes a little bit lenient and allow you to draw the diagrams. But to be honest, because you need to, I guess with pentane, you could write it out. But just to be on the safe side, because it says right, I'd probably stick with writing. And then good, yep, so it's producing carbon dioxide and water as normal, and then we just need to balance it. So again, as I said before, we can have X plus Y over 4, lots of oxygens, so that makes 8 oxygens. X numbers of CO2s, which would be 5, and then Y over 2, lots of H2O, so that would be 6. And that gives us our full mark, and it has to be completely balanced for the full mark. And then, so well done to those of you that got that right. That looks like pretty much everybody, so really good. Yeah, exactly, Dominic, that's what I was thinking. So you could draw out the C5H12, I guess, if you were unsure what the formula would be, but you couldn't then balance your CO2s and your waters because you'd have to draw out lots of molecules, so that would probably be not a very good use of your time, I would guess. Okay, and it then says, identify the type and number of bonds broken and formed during the combustion of a molecule of pentane. So identify the type and number of bonds broken and formed during the combustion of a molecule of pentane. So this is a slightly different side step. We're looking at 1, 2, 3, 4, 5. What bonds are made and broken during combustion? Well, we have to think about every single bond being broken. And we also have 8 lots of O double bonds, oxygen doubly bonded to oxygens. No, these are the bonds. We're not talking about the intermolecular forces. We're talking about the actual bonds that are broken when combustion happens, because combustion is a chemical reaction, not a change of state. It's an actual chemical reaction, so we do have to break bonds. So let's just count them then. So there's 1, 2, 3, 4 lots of C-C bonds. So just check that you're happy that it is only 4 bonds there. There are 12 lots of carbon-hydrogen bonds. And again, just count them and just check you're happy. And then there are 8 oxygen double bonds that are broken. And then ones that are made, well, we make 5 lots of C double bond O and 6 lots of H2O. Oops, that's supposed to be a double bond. So that means we're going to get 10 lots of C double bond O's broken and 12 lots of OHs broken. Sorry, I said broken, I meant made. Made. And again, you have to get all of that right for 1 mark each to total the 2 marks. So carbon-carbon covalent bonds, yeah, they are covalent bonds. So if we're just to identify them, we'll leave this question for now. Just to identify them, we can count 1, 2, 3, 4 carbon-carbon bonds. In order for this molecule to break up, we have to break, for example, all 4 of those carbon-carbon bonds. 1, 2, 3, 4 broken, and then the same but with our carbon-hydrogen bonds, but this time there's 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them. And exactly the same, we've got oxygen-oxygen double bonds. There are 8 oxygen molecules, and we have to break all of the oxygen-oxygen double bonds. So that means we have to break 8 oxygen-oxygen double bonds. Yes, these bonds are covalent. Yeah, they are all covalent bonds. Lovely. Right, I've only got 4 minutes left, so I'm just going to pause that there. So thank you to everybody who is here. Just to finish off with, just to say, hopefully now you guys are happy with understanding trends in boiling points of alkanes, recalling the processes of fractional distillation and cracking, and recalling the equations for combustion of hydrocarbons and other pollutants. Just so that you're aware, we've got some more web classes coming up. We've got maths next week. We've got then another A-level chemistry class, then A-level physics, then A-level biology. So please feel free to set a reminder on YouTube to remind yourself to come and get them. And we have our A-level chemistry tutoring, which is available on the website. So I'm just going to let you know about that now. Please don't forget that you can use the code tutor7 at checkout to claim 1 week free trial. But these what's it called? Code is going to expire in 24 hours. So if you're going to use it, you need to use it soon. Yes, these sessions are recorded. You can find them on the YouTube site. And if you join us on SnapRevise on the website, then actually we share, we record all of our sessions and share. I'm just trying to share with you. There it is. We record all of our sessions, and then you can watch them back at a later date as well. So here we have the A-level chemistry tutoring, also the SnapRevise A-level tutoring website. So if you have a look, if you go onto this website and click in the top right-hand corner, you get the option of finding tutoring. So if you go onto tutoring, then it gives you all the information about our tutoring that we have available. So you would pick whichever topic you're interested in. So let's say A-level chemistry. And then on the A-level chemistry page, you can see which exam boards we offer, which is usually all 3 of them. We do at least 4 sessions a week. We cover every topic, and there are some top-rated tutors, even if I do say so myself. We have a high-quality structured program and interactive and engaging lessons. And if you scroll all the way down to the bottom, you can see some free sample classes to have a look at and to download. And then there is the schedule, which tells you all of the classes that are coming up for the next couple of months. So you can see what you'd like to come to, what you'd like to look at. Yeah, you can I'm sure you can cancel at any time after the trial. You get 1 week of all of the tutoring. So let's look at next week. If you go to next week, we would have, if I scroll down to the bottom, so you can see all of these are recorded. So that means if you were part of SnapRevise, you could click on that and see the recorded lesson. So for next week, starting tomorrow, there would be a lesson on addition polymers with Georgia, then a drop-in tutor session with me, and then let's go back to April. Then we have a year 13 aromatics class with me, year 13 letters, enthalpy and solvation with me, and drop-in tutor with me as well. So these are, no, I don't have my camera on. Sorry, at the moment, I just don't want it to freeze. So please feel free to have a look. The 2 different types of classes are a web class, which is just like a lesson like this one, or a drop-in session, which is a tutoring session, which allow you to ask your own personal questions. You can submit questions that you want answered, and we'll go through those questions with you. And everyone's welcome to join, and you can ask as many questions as you like. And yeah, it's a really good way for you to get your personal questions answered and for you to just practice what everyone else is finding difficult. So please have a look on that. So I've turned my webcam on just to say goodbye, just and in the hope it doesn't freeze. But have a lovely rest of the day, guys, and I hope you've had a great tutoring session, teaching session with us, and hopefully I'll see you again on a future web class. Oh, sorry, yes, we don't have cameras on during tutoring. We have ours on, I have mine on, but you guys don't. It's just chat, so you don't have to worry about that. You just interact via the chat. Okay, Have a lovely rest of the day then, guys, and I will see you all soon. If you have any questions, please just send it to hello@snapprovides.co.uk, and we'll try and get your questions answered. Okay, thank you very much, guys. Lovely to see you, and I will see you soon. Cheers. Thanks, guys.